Hello everyone, welcome to my paper presentation. I am MD Rafiqul Islam Robin, a computer science PhD student at the University of Houston. I will now present our paper, Study of Distractors in Neural Models of Code. In this paper, we present an alternative perspective of input features called distractors that consider the confidence of model in its prediction. Understanding distractors can provide a complementary view of the feature's relevance and improves the interpretability of models in its prediction. This is a joint work with my colleague Aftab Hussain and my PhD advisor Muhammad Amin Alipur from University of Houston and our collaborator Shahil Sunaja from IBM Research. In recent years, source code analysis using deep neural networks has gained mass popularity. It becomes possible because the publicly available source code repository contain a large amount of programming data, and deep neural networks with its capacity can capture complex patterns from programs. Having these properties, a researcher can now train various deep neural networks to process source code for solving different code intelligence tasks, including code generation and vulnerability detection. This is an example of software vulnerability detection task where a bidirectional RNN model takes a program as a sequence of tokens and predicts whether the program contains any vulnerability. This one is the example for variable misuse, locate and repair task. This task utilizes the transformer model. Given an input program, the model predicts whether the program contains a variable misuse bug, then the pointer to the location of the buggy variable and its corresponding correct variable. Another popular models are code2vec and code2sec for the task of method naming prediction. They use AST path-based code embeddings for predicting method name. And the CodeBird model, which is a BERT-based bimodal model that can process both code and text and can handle a group of tasks including code summarization, code generation, and semantic code search. Although deep neural models can handle varieties of software engineering tasks, one important concern is they are opaque black box. We barely know about what input features actually they learn from the program for making their target prediction. It becomes more challenging because different models process programs differently, use different neural architectures, and output differently based on the target task. Therefore, understanding and extracting key insight into the features that model use in making predictions becomes an active area of research. Various techniques have been proposed to improve the transparency and interpretability of models prediction. One popular approach is using the attention score to highlight the significance of different code elements in the prediction of model. Although it might helpful for attention-based model, it often requires access to the models to save the attention score for each component of program, which is sometimes difficult to obtain from a fully black box model and when model use complex embeddings rather than tokens for generating code embeddings. Another way is to part up the element of program and observe the impact in the model's prediction to understand the potential significance. However, sometimes this approach needs expert knowledge to choose effective perturbation technique or use gradient-based approach to apply perturbation that requires access to the model. Therefore, reduction-based approach becomes familiar for identifying important tokens that relate to the model's prediction. Unlike other approach. This approach does not require access to the model's parameter or expert knowledge. It only prunes the input step by step and observe the output of the model. We will base our experiment on this reduction-based technique and will discuss in details in the following slides. This is the high-level overview of the program reduction workflow for improving the interpretability of the model's prediction. This approach adopts a program reduction technique to remove a portion of code snippet from input program and creates a candidate reduced program. The approach then checks if the reduced program is valid based on the target task and programming language. It then compares the prediction of model between the reduced program and input program. If the reduced program is valid and preserves the same prediction, it continues reducing the current candidate. Otherwise, it creates a new candidate for processing. And it continues until it finds the final reduced program, where it cannot remove any further tokens without altering the model's prediction. Finally, by observing key features from the reduced program, we may better understand the reasoning behind a model's prediction on the actual input program. We experimented with two reduction algorithms. One is token-based delta debugging and another is tree-based parses. The delta debugging is a syntax-aware program reduction algorithm. It systematically removes token from an input program for finding the final reduced program. Given an input program P and a model M, it first records the target prediction Y given by the model M on program P. The delta debugging then produces a candidate program by removing some parts from the original input program. If the reduced program does not provide the same prediction Y, it then rejects this candidate and creates another candidate by removing some other parts from the program. And the reduction steps continues if it preserves the same prediction Y. It then iteratively searches for reduced program that produce the same prediction as the original input program, and step by step it reaches to the final reduced program. The final reduced program is on minimal, where any attempt to further reduction will change the model's correct prediction. Another way to reduce program by traversing the tree of the program using parses. While delta debugging is syntax aware, parses follow the grammar of programming language for reducing programs. Similarly, given an input program and a model, the approach first records the target prediction Y given by the model M on program P. After that, parses parse the input program into a parse tree. Then it traverses the tree node by node and determine whether a tree node is deletable, depending on whether it preserves the same prediction Y. It repeatedly checks the tree node and prunes the subtree where node is deletable, and the remaining program is the final reduced program R that produces the same prediction as the original input program. In this slide, we will show an example of program reduction. This is a sample program that takes an array as argument and performs sorting of the array elements. It uses loop, array element condition checking, and value swapping for performing the sorting function. A trained model such as Code2Vec can correctly predict this program as sort function. If we remove the value swapping part, the model still thinks it is a sort function. After removing the array element condition checking, the model still predicts the code as sorting function. Eventually, after removing the inner and outer loops, the model still decides to consider the remaining program as sort function. Clearly, the model is not using the full context from the code, like looping element checking, or the value swapping. It only needs the information about the array argument and the swap control variable to recognize the code as a short function. Maybe the model has seen a lots of program with these variables, so it thinks these variables are more important than other code elements of the prediction. Such prediction preserving program reduction can give us an intuition about the model's inference, and such kind of reduced program has various applications. For example, we can use the reduced program to better understand the model's prediction. This program is on-get function of the Android activity. It has a override function with the same name and the set content view API call that activity used to attach a view. After reducing program with a model, we can observe that the model uses the information about the view to recognize this code as a Android activity on-get API. While another model rely on only the override name leakage to detect the on-get function. Therefore, by observing reduced program, we can understand what features a model is actually using from input program for making their target prediction. We can also use the reduced program to verify the model's prediction. For example, this program is a buggy program that contains a array out of bound exception. And this is the part of program that a model consider as buggy, where the true bug is exist in the reduced program. And this is the portion of code that another model consider as buggy, but the correct bug is not present in this reduced program. So in this way, by comparing the existence of true bug in reduced program, we can verify whether the model is learning the correct signal. However, the previous works mostly consider the predicted level and ignore the consideration of model's confidence. The confidence of model, which is often represented as a probability score, indicates how certain a model is in its prediction. Therefore, in this work, we consider the probability score to interpret the prediction from a different angle. A model may preserve the predicted level, but it can change its probability score in its prediction. We mainly aim to study what features cause doubt about a model's prediction by affecting the model's confidence. More precisely, we define the notion of distractor tokens, where the confidence of model in its prediction changes significantly when such tokens are removed from the input programs. In this slide, we will show example for distractor tokens. For example, this program is an implementation of prime number checking function. If we remove the condition that check the corner case of valid positive numbers, the model increases its confidence score by around 10%. But removing the stopping condition decreases the confidence score by more than 20%. However, removing the iterator increment has negligible effect in the model's probability score. So the model might think the stopping condition is more important than the iterator increment, but the valid number checking was obvious to prime calculation and removing it increases model's prediction. And removing the modulus operator misclassify the model prediction into a different predicted level, because this modulus operator was an important part for prime number checking. Therefore, by observing and identifying the effect of distractor tokens, we could depict the interpretability of model's prediction from a different perspective. Here is a more detailed step and explanation for identifying the distractor tokens. Given an input program and a model, We record the predicted label and the probability score given by the model on the input program. Then using determine algorithm, we produce a reduced program by removing some tokens from input programs. And then we record the predicted label and probability score given by the model M on the reduced program. After that, we compare the probability score of input program with the probability score of reduced program for understanding the impact of token removals from input program. If the removing tokens significantly change the model's probability score, then these tokens are considered as distractor tokens. In this experiment, we consider a token as distractor if removing it from input program increases or decreases the probability score of model by at least 10%. We conducted a detailed experiment with 4 different tasks using 7 different models across 4 datasets of 3 programming languages. In the very beginning, for observing the effect of Distractor on task and model, we studied the sample that yielded a noticeable probability change during the reduction steps. We consider the sample that were impacted by at least 10% in the probability score and compute the average value of this change along with the max change in both probability increase and probability decrease direction. On comparing the model's probability increase and probability decrease value across different model of different task and dataset, we can observe that the code-to-bake model has the highest max and mean value for both probability increase and probability decrease. On average, the code-to-bake model is comparatively more susceptible to distractors than the other models in our experiment. In this research question, we analyze the level of distractor that cause a significant change in the model's confidence. We mainly examine the maximum probability increase and maximum probability decrease in the model's prediction score change. The x-axis in those figures shows the number of samples we consider in this experiment. We sorted those samples based on maximum probability change to better visualize the extent of probability change among models. Figure A illustrates the highest probability increase observed during the reduction process of the sample, while Figure B demonstrates the highest probability decrease. According to this figure, we can observe that the RNN and transformer model of variable misuse task have the highest value for maximum probability increase and maximum probability decrease compared to the other models in our experiment. And the codebird model using the code search dataset have the minimum maximum probability increase and the minimum maximum probability decrease compared to the other models in most of the samples. On the other hand, the model of method name prediction and the model of vulnerability detection appear in the middle in the both maximum probability increase and maximum probability decrease experiment. These results may indicate that the codebird model for code search task has comparatively strong reliance on overall program tokens than other models. Therefore, removing a tokens introduce comparatively lower value in maximum probability increase and maximum probability decrease in most of the samples for codebird model. On the other hand, the Vermeer's models might make decision relying on more specific tokens, and removing those tokens can cause high prediction change. We next study the category of distractor tokens that were removed from input programs in reduction steps. And this table shows such most popular distractor tokens. The vulnerability dataset was normalized and we have found a total of 16 unique tokens that were removed from input programs. Therefore, we also highlighted top 16 common distractor tokens for other models and tasks. We can observe that these distractor tokens can be divided into a variety of categories such as control flow, data type, digit, identifier, operators, and other syntax-specific tokens. And the control flow contains condition, loop, and return statement, and data type contains integer, character, and string data types. And there are some syntax-related tokens such as new line and indentation for Python, and override and semicolon for Java programming language. So it may highlight that the token from a variety of categories can play a significant role in the model's confidence, and models seem to be impacted by the similar categories over all dataset and tasks we experimented in our study. Although distractors can provide complementary view to improve the interpretability, in some cases it might introduce challenges to explain. For example, in figure A, the removal of throw and new token while the exception condition is present in the code does not provide any concrete meaning. Similarly, when the input code is incorrect or incomplete, such as the equals method in figure B, the probability change for removing a token is hard to explain. A more systematic approach for applying and identifying destructor tokens and comparing it with respect to highly attribute tokens may provide any additional information. And we plan to study those in our future work. In summary, deep neural models are increasingly being used for processing source code related tasks, but these models are highly black box. We barely know about the input features they use for making prediction. Therefore, different techniques are used for improving their interpretability, and we consider the probability score along with the predicted level to interpret the prediction from a different perspective. We conducted our experiment using different task model and dataset and demonstrate how Distractor can help to improve the interpretability of models prediction. For preprint and artifacts of our study, please check this resource, and thank you for your attention.